size must be less than or equal to the total inventory which allowed over here. In order to find out the optimum value of Qi, we can minimize the function k over there. For that we need to use the Lagrangian function over there. For that we are going to define a Lagrangian function over here, that is nothing but L of Qi lambda, where Qi is a decision variable over here, lambda is also decision variable over here, that is equal to nothing but the total cost plus Lagrangian multiplier multiplied with the constraint over there. Our constraint we know that is summation Qi by 2 less than or equal to n. From that we are having this equation over here. So now this is the objective is to minimize this function L of Qi lambda according to the value of Qi and lambda over there. So for that we need to use the concept of calculus over here, and for that is nothing but del L by del lambda equal to 0 and del L by del Qi equal to 0. From that we are having a relationship between Qi and lambda in the form of that Qi is nothing but square root of 2 ai Ri upon Hi plus lambda. We have an example of a small factory which produces 3 items, say 1, 2 and 3, and it has a limited of storage capacity sufficiently only for 500 units for all type of items. So we are having that capital N is equal to 500, right? We are having some information about the first, second and third product in form of total demand per unit per year, purchase price per unit, as well as ordering cost over there per unit. The inventory carrying charge that we are considering over that is nothing but 20% of average inventory valuation per month for each item. If the stockouts are not allowed, that means shortages does not occurs over there. Determine the optimal lot size for each and every item. If we ignore the constraint that we are having over there, and if we work out for the usual EOQ model, then we can obtain for the first item Q1 to be 346 units, for the second item Q2 to be 250 units, and for the third item Q3 must be 447 over there. If we apply our constraint over here, that is nothing but your right hand side, that is summation of Qi by 2, if that will gives you the value 521 units. But we know that we are having a capacity up to 500 units only, so we are having a 21 units more over here. So we need to work out for the Lagrangian multiplier method. It is nothing but just a trial and error, one kind of a trial and error method to find out the optimal value of lambda over there. So starting with the value of lambda is equal to 1.
Q1 is equal to 245 units. For second item it says procure 200 units, and third item it is 387 units. So on an average it says inventory level is 416. This shows that the average inventory level is less than the available storage limit of 500 units. So this will not work. So let's see for lambda is equal to 0.1. Then we get Q1 is equal to 316 units, Q2 is equal to 230 units, and Q3 is equal to 435 units. So on an average 491 units turns out to be on an average inventory level. This inventory level no doubt is very close to the available limit of items, and hence this can work as a optimal solution. But one can try with 0.11 also, or you can try with 0.12 also. You will come more and more nearer to the available capacity. So on an average, you are looking at the formula for getting QIs. What we said here, square root 2 ai Ri upon Hi plus lambda. We can make a judgment whether to increase lambda or whether to decrease lambda. So let's have in terms of remark, if you increase the value of lambda, if the value of average inventory is less than the available inventory. That because it goes on indirect proportion. So if one increases, second one will decrease, and vice versa. Okay. Now let's see problem of EOQ with investment constraint. Okay. Suppose I have only investment constraint, then how should I use Lagrange's technique? That is what next problem is. Inventory represents a substantial investment capital for many firms. Thus, the decision maker places a limit on the inventory to be carried out. If very costly items are to be procured with less costlier, then we need to procure only few number of items which are costlier than the other group. For example, if it is plasma TV versus simple TV, then plasma TV is costing 75,000 while normal TV is costing only 34 to 37,000. So obviously we'll put smaller order of plasma TV than the usual one. So the inventory control policy must then be adjusted to meet the objective if total investment exceeds the limit. So in this case, we'll have to work with the purchase cost, because as my example said, plasma TV is much costlier than the normal one. So costlier in the sense what? Purchase cost. So let's see if CI is the cost per unit of the item for all the n items, and F is the total fund available to be invested on the inventory. When we have total purchase cost for ith item turns out to be CI QI, and for all the n items it is sigma CI QI. But fund available with the firm is only F revenue, F rupees you can say. So what my constant turns out to be sigma CI QI to be less than or equal to F. So problem is to minimize total cost subject to the investment constraint, which is sigma CI QI less than or equal to F and QI to be greater than or equal to 0. So in order to find the optimal value of QI so as to minimize K, we construct Lagrange's function which consists of total cost of n items plus lambda times, that is Lagrange's multiplier times the constraint. The optimal value of lambda, as usual, as we did in the first two problems, we differentiate Lagrange's function with respect to decision variables, that is lambda and QIs, where I can be any number 1 to n, and that says that total cost will be optimum, that is minimum, when my total fund available will turn out to be equal to sigma CI QI, and if I procure quantity square root 2i AI 2 AI Ri upon Hi plus 2 lambda Ci. So if you look at the Qi, denominator says that Lagrange's multiplier and purchase cost both are constrained. Let us have one example.
That consider a factory which produces three kind of items over there in lot. The demand rate for each item is considered to be constant. It is assumed to be that it is a deterministic. No backorders are permitted over there. The data is given as follows for the three items, first and second and third, and that is in the form of demand rate, purchase cost, ordering cost and inventory holding cost over there. According to with that, we will move to find out the optimal lot size when the total investment does not exist rupees 1000. That means we are having fund of 1000 rupees only, and for that we need to work out for that. Ignoring the constraint we are going to use our usual EOQ model, and from that we can find out the value of Q1, Q2 and Q3 for the first, second and third item respectively in as 224, 219 and 212 respectively, and that will give you the total cost to be 1968.50 rupees over.
That gives total investment at any time is 1968 rupees 50 paisa,
which is more than the maximum fund we are having, because of we are having 1000 rupees only to invest over there, and therefore we need to use Lagrangian multiplier technique over there. For lambda is equal to 1, we can find out the value of Q1, Q2 and Q3, which is turns out to be 177, 168 and 173 respectively over there, and that will gives our total investment to be 1551.50 rupees over there, which is still larger than 1000 rupees. So we need to go for the lambda is equal to 5. This is just a trial and error method, so we can use lambda is equal to 5 also. That will give you the total investment to be 979 rupees, which is less than 1000. And we will go for lambda is equal to 4. From that we are having such an information about the Q1 to be 121 units, Q2 to be 112 units and Q3 to be 123 units. That will gives me the total investment to be 1112.50 rupees over there, which is still larger than 1000. Hence the best value of lambda lies between 4 and 5. That we can make a judgment over here. So we'll try for 4, lambda is equal to 4.7. So that will gives me the total investment to be 999.50 rupees, which is as nearer to 1000 rupees. So this is my best optimum solution over here for that,
which will minimize the total cost. And here what Professor Sukla said, for lambda is equal to 5, he said it is 979 total investment. For lambda is equal to 4, it is 1112.50 rupees. So in for lambda is equal to 4 it increases, for lambda is equal to 5 it decreases. So I said that looking at the formula for Qi, one can make a judgment whether to increase the value of lambda or decrease the value of lambda. If your total fund turns out to be more, decrease the value of lambda, or vice versa, and that what has been used here. Okay. Next is problem of number of orders constraint. With some manufacturer, because of some production facility available with them, this constraint comes up. It is only I can place an order of 5 numbers or 10 numbers in a year or in a stipulated time. So in that case, what should be the problem? No doubt we won't have any optimal solution, but we can consider reasonably good solution that what in maths we said or operation research we said it turns out to be most favorable or suboptimal solution to find EOQ in case of multi-item inventory problem with a constraint on the number of orders per year. This technique can also be used where ordering cost per order and carrying cost per unit per time unit period are not known. Sometimes it such happens that ordering costs and inventory holding costs may fluctuate in such a way, or it fluctuate in very small amount that we can consider it to be a negligible quantity. So in this case, the method which we'll have next will give you optimal solution, or in general we'll say suboptimal solution. It works with two assumptions. First one is ordering costs and carrying costs are same for all the items. So we assume that ordering costs will be same for whatever number of items we store, and same is with carrying costs. Orders are received in lots, demand is constant, and stockouts are not allowed. So in this case, the total number of orders per year, as we had in last lecture, is given by R by Q, whatever demand is and whatever procurement is there. If you have demand of 1000 units and in each lot you are procuring 100 units, that means you have total number of orders to be 10 in the given cycle time for all the items, will be given by sigma root RICI upon sigma RICI into R by Q, where notations are similar. What we are starting from, R as the demand in units and C is cost of items in rupees. C means CI and R means RI. Let's see, is we don't have any good method to work with, but I can explain you with the help of an example how it works. A company has to purchase 4 items, say ABCD, for the next year, and the predicted demand and unit price are as follows. So from the past experience, the manufacturer or producer has predicted that this will turn out to be the demand of particular item, and this may turn out to be the unit price of the particular item. We have 4 items. Demand of items are 60,000, 40,000, 1200 and 5,000, whereas purchase costs are 3 rupees, 2 rupees, 24 rupees and 4 rupees. If the company wants to restrict the total number of orders to 40, so only company can order for 40 times for all the 4 items, that is cumulative number of orders are 40. How many orders should be placed for each item? And obviously, as we had said before also, if the items are costlier, we'll put order in the smaller quantity, and if they are cheaper, we'll put order of more quantities, provided there is sufficient demand. So how this problem can be worked out? You have items, first, second and third column is the given data. Fourth column is you can just multiply RICI and have its square root. Sum it up, that is 1018.22, that is the last horizontal row. And then we said that crude method says you work out for each item ratio of root RICI upon sigma root RICI. That gives you 0.416 for the first item, for the item A, 0.277 for item B, 0.166 for item C, and 0.138 for item D. Multiply this with number of orders, which we said is 40 in all. So multiply fifth column with 40 and you can get the number of orders. So 0.416 when multiplied with 40 gives you, and it is approximated to the nearest integer quantity because number of orders cannot be fractional. So for the first item it says put an order of 17 units. For second item, that is for item B, put an order of 11 units. For C items, put an order of 7 units, and for D it is 5 orders. So if you sum up last column, it turns out to be 40. Not necessary that every time it will turn out to be 40. It may slightly vary, but you will come nearer to it, whatever is the restriction on number of orders that has been specified by the problem.
Now we are moving for the dynamic order quantity that we have discussed in inventory problems when the demand is uniform, but in the real situation it is not turns out to be correct. Sometimes we come across a non-uniform demand such as rising trends or falling rate trends, or maybe both. Seasonal influences are there. When the demand is known but have irregular lot sizes, proceed as follows. As for example, we will start with the for each period we will start with n. Consider the condition that n square into r n plus 1, which must be less than or equal less than a upon h, where a is the setup cost, which is ordering cost, and h is the inventory holding cost associated with a particular item over there.
And r of n plus 1 is the demand for the next period.
If the above conditions is satisfied, increase the value of n by 1. You can find out the next period into the consideration. But if the condition is not satisfied, then an end of the particular grouping and the following period is taken to be with starting with a new period 1 2 there, and then proceed on over there. If we are given such an information like the monthly demand of a schedule of a product is given as follows. In a first month its demand is 200 units, in a second month 300, in a third month 20 unit, in a fourth month 140, in a fifth month 180, likewise up to 10th month it will turns out to be 270 units over there. Setup cost is given to us, that is nothing but 360 rupees over there, and cost of a particular item is considered to be 15 rupees, and the inventory charges are considered to be 2.5% of annual average inventory value of that, but average inventory value is given to be 15 rupees over there, and so it will be nothing but 2.5 multiplied with 15 over there. So to find out the optimal plan of the batch size, we will proceed as A is equal to 360, H is equal to 15 into 2.5 as I said, and so from that we are having the value of A given H to be 960 over there. Using the above information we get the this following representation, like in a
this table says first column is for months, second column is for demand, which we are given. Now we have to start with n is equal to 1, as Professor Sukla said. When n is equal to 1, fourth column is I need to work out what is n square rn plus 1, and if it turns out to be less than a by h, which we had as 960, we'll continue with, otherwise we have to change the grouping. So let's have first group. In first row Rn plus 1, that is the demand of the next period, that is next period means second year, which is 300. So 1 square into 300, so n square Rn plus 1 turns